Hello, ladies and gentlemen. My name is Junjie Shentu, and I'm from Durham University. I'm glad to present my study in WACV 2022, and the title of my study is CXR-IRGen, an integrated vision and language model for the generation of clinically accurate chest X-ray image report pairs. My presentation can be divided into 4 sections. First, background and methodology and experimental results, and finally, conclusion and future works. Here comes the background. According to the data released by NHS UK, X-ray tests are the most common medical imaging tests in England. There are 22 million X-ray tests performed in 2022 to 2023. And among the X-ray tests, chest X-ray test was the most commonly requested by GPs, and there are 2.1 million tests performed during 2022 to 2023. Such a huge amount of chest X-ray tests put huge workload on the radiologists, given the current shortfall of 33% in the radiology workforce across the whole UK. On the other hand, the deep learning techniques can assist CXR image diagnosis, but the amount of training data is seriously limited. There are a few reasons for this. First, there are strict privacy protocols. Second, some data are very scarce. For example, in the early stage of COVID-19, it was really hard to acquire positive COVID-19 CXR images. In this regard, deep learning models, such as GANs and diffusion models, can generate high-fidelity CXR images, which can augment the current CXR dataset. However, CXR data usually contain image and report pairs, but the existing studies commonly focus on single model data, so it is really worthwhile to propose a model that can jointly generate CXR images and reports. Based on the diffusion model, we propose chest X-ray image report generation, namely CXR-IRGen. CXR-IRGen follows a modularized architecture, which includes a vision module and a language module. We also propose a novel design of prompt that combines the text embedding and the image embedding of a reference image that has the same label as the input. The figure below shows the inference process of CXR-IRGen. Then we are going to introduce the training process. For the vision module, we fine-tune the pre-trained diffusion model with the newly designed prompt, and we test the new prompt with 2 backbones, the convolution-based UNet and the transformer-based UVIT. Both backbones have skip connections between shallow and deep layers. For the language module, we adopt a 2-stage training for CXR report generation. In the first stage, we use a pre-trained large language model with an encoder-decoder architecture. Here we use BART. We first encode the original text into a sequence of text embeddings, and then get averaged embedding. Use it as input for the decoder to reconstruct the text, and compare the cross-entropy between original and reconstructed text. In the second stage, we use a prior model. Here we use vision transformer to project the image embedding produced by the vision module into the corresponding text embedding, and we minimize the mean square error and maximize the cosine similarity between the projected and representative text embedding. For the dataset, we use Mimic CXR, which is a large-scale CXR dataset including over 370,000 CXR images, with over 180 being captioned. As for the evaluation metric, for image, we use FID, PSNR, and SSIM to evaluate the general quality, and AUROC value for clinical efficacy. For report, we use BLUE and ROGUE-L to evaluate the general quality, and F1 score for clinical efficacy. We train UNet and UVIT backbones for 10,000 steps, get checkpoint for every 5,000 steps, and generate 1,000 images for evaluation. The results show that adding the reference image embedding can improve the general quality of generated images, especially for UNet backbone. Here we can find the reference image embedding helps improve all the metrics for UNet, but only FID for UVIT. We hypothesize it is because we use different strategies to combine the embeddings. For UNet, we append the reference image embedding to the text embedding. However, for UIT, we take the average value of text and reference image embedding. Thus, there might be some information loss. Besides, we choose 5 pathologies and generate 500 images for each pathology as well as a no finding label. We further use a pre-trained classifier to perform a binary classification task on the generated images, including the healthy images and unhealthy images, and calculate the AURC value. It can be found that adding reference image embedding can also enhance the clinical efficacy of the generated images. For the evaluation of CXR report, we apply the report generation models on real CXR images from MIMIC dataset and calculate the matrix on generated reports. It can be found our model achieves state-of-the-art results in both general performance and clinical efficacy, and the variant trained jointly on finding and impression sections achieves the highest F1 score. It should be noted that the baseline model M2Trans image encoder is additionally trained on the CheckSpert dataset, which is another large-scale CXR dataset, which may enhance the CXR report generation quality and result in an unfair comparison. We further apply the report generation models on CXR images generated by our vision module. Among the images generated by 4 variants of the vision module, our model, trained jointly on findings and impression sections, achieves the highest F1 score on 3. Therefore, it can be concluded that our model can generate clinically accurate CXR image report pairs. In conclusion, our proposed model can generate clinically accurate and consistent CXR image report pairs, and the novel prompt design can enhance the quality of the generated CXR images. As for the future work, we plan to request radiologists to evaluate our synthesized CXR data and give some professional feedback. That's all for my presentation. Thank you for your listening.